report this dotted line, which is actually very controversial in IPCC world, and it captures the fact that there are processes that we still don't understand, and there is a deep uncertainty into our projections. So sea level in the US will matter too. It's a matter of national security when you think about it too. It's a matter of economic part because a lot of cities on coastal regions, but in terms of securities, a lot of army and ports are on the sea. So it's a big problem whether or not you believe in climate change. Sea levels are rising and we need to do something about it. So let's see. I know that I've understand that you've had some previous speakers that talked to you about ice sheets. So I will give you a very small overview in case you had missed it or never seen it, that basically we know from satellite observations that sea level, that the ice sheets are losing mass. We know, and this is an image from GRACE. GRACE is a fantastic satellite. It shows you the total mass change. It shows you the variation up and down because of the season. There's more snowfall and mass loss in the summer melt. But in general, the Greenland ice sheet is losing mass as a trend. And so the sea level is increasing from both the Greenland and Antarctic ice sheets. We also know that the ice sheets are really big. And if all of the ice melted, you could have actually a lot of sea level. And so those what the images on the other side of this image show you for the Greenland and Antarctic contribution. But it's not a problem that, I mean, it's a problem that we have to worry in the future. I mentioned, like, in 100 years time scale, it will become important for the US too. But it is a problem right now in our society, but also in the small island nations, right? And so this is one of a fascinating photo of, not fascinating, but for me, it's a photo that really helps again, think about my work, put my work into perspective when I sometimes get really frustrated about many aspects of my work. I look at this photo, my grandmother's photo, because to kind of think that right now you're having small island nations. So this is the Prime Minister of Tuvalu, who is during COP26 addressing the participants of COP, and in actually his environment, which is being flooded, and this nation is disappearing. And the part that is really striking for me about this kind of work is now the UN has a partnership to help relocate small island nations. And they're asking the NASA Sea Level Change Team, which I'm helping co-lead, to write reports for different nations on how sea level is going to change for them. And it's used in negotiation and in relocation of small island nations. So it's a problem that is a real problem that is affecting population worldwide. So was it always this? I mean, were ice sheets always known to be a potential source of sea level? Well, if you think back about the ice sheets and how they were represented into the IPCC cycle, so the IPCC makes those reports every few years about the state of the climate. The first few assessment reports in the 90s and 2000, well, basically the understanding at the time was that we knew everything and there was no expected major dynamic contribution from the ice sheets expected for the 21st century. The main contribution of sea level rise was going to be thermal expansion and the melting of glaciers. And so at that time, I was doing, at the time of the third assessment report in 2001, I was just ending my undergrad, starting my master's program. And then you can see in green, in blue, you have the Greenland ice sheet contribution. In purple, you have the Antarctic ice sheet contribution. And you can see that basically those contributions sometimes balancing out, sometimes Greenland always was, the climate model were always projecting Greenland to lose mass. Antarctica is more tricky because in a warming world, you may have more accumulation projected by the climate models. And so that's why you could actually have a drop in sea level with those models. Now we move forward to the fourth assessment report, which was really, really damning for the ice sheet modeling community, because you had the statement that understanding of the recent observations that we were seeing at that time, you had new satellite that had just been launched, and they were taking amazing measurements over Antarctica and Greenland and showing that the ice sheets were very dynamic. They were not giant snowball like the previous IPCC assessment had kind of assessed and kind of understood as. So the observations kind of really between the IPCC third assessment report and fourth assessment report really changed the way that we understood ice. It came from that, ice were really actually very, very dynamic and could lose mass very rapidly. Yet the models could not actually reproduce this change. And so we went from we know everything about sea level to we know nothing at all because the models can't produce the observations. And at that time, when the fourth assessment report came out, I was in London just finishing my PhD. So then we arrived to a few years later, the next assessment report. We went to we know everything, to we know nothing, to we know something, but not enough. The reason we know something is basically because there is improved modeling of ice sheets, which is great. However, there remain a lot of uncertainty, particularly related to the magnitude and rate of ice sheets contributions. And at that time, I had moved to the US. I was now a civil servant at NASA Goddard Space Flight Center. It was, so 2013, it was the end of the Sea Rise effort, which was the first community effort of ice sheet modelers coming together to try to make some type of coordinated, not projections because we didn't have the right forcings yet. So, but we were examining sensitivities of the ice sheets in similar experiments to increase atmospheric and increase ocean forcing. It was, and I talked to the students at lunchtime today, it was one of the hardest things I had to do in my life because I had come from a PhD that was looking at very improving models with like full Stokes model, grounding line physics, to working with those large ice sheet models that couldn't do grounding line, that had massive boxes, that didn't have ice shelves. But it was community driven. And the first time that I realized that you could actually, there was a lot that could be done as a community. And the thing about the fifth assessment report that we don't really often talk about, and that's very instrumental to ISMIP 6, is that at the same time as a sea rise was going on and targeting improved knowledge of the ice sheets to the fifth assessment report, you had a European effort that was called Ice to Sea that had a lot of money. They were trying to do sea level projection using regional climate models and ocean modeling. And there was a very tight-knit group. And basically, there was an infighting between the European community that was close-knit and had very powerful model, and the American-led effort that had no money and that was community-driven, to the point where the IPCC cycles actually have deadlines of acceptance of papers, that if you don't get accepted by a certain time, you cannot be in the report. This infighting of the community meant that the sea rise papers actually got rejected at the last minute. And the community at the time of the fifth assessment report was really not very healthy. There was a lot of infighting, and CLIC, the climate and cryosphere, kind of came to us and kind of said, okay, this is not very good. We need to kind of find a way. And that led to ISMIP 6, right? Where basically we brought together the European community and the American community had a workshop at Goddard and decided, okay, we can't do this in fighting anymore. This is no good for anyone. We have to work together to kind of get the best projections of sea level that we can do. And so we learned from each of our efforts to deliver ISMEP. It's an incredible group of scientists. We started in the Red Star in 2014. There was this workshop I just mentioned, and we went all the way to the IPCC report in 2020. So you can count the years. The little different stars were highlighting where we could meet for free because we had no money, as Ginny said. And so we were meeting at AGU. This is the purple triangle. We were meeting at EGU. This is the yellow triangle. We had hoops that we had to do. Those are all of those little stars, those little arrows, because like to be part of a MIP for CMIP, you have to be endorsed by CMIP. So you have to write a proposal and you have to have climate models to kind of say, yes, I will do the effort. And so we had to have those signed. And then we had to have something, I can't remember what, but there was like lots of very, very rigorous hoops that we had to do. And then we kind of went to this kind of crazy thing about trying to do the ice sheet models getting ready together. And so we had an effort that looked at the initialization of ice sheet models for Greenland because we could do that without any climate forcing. And then we did the same thing for Antarctica in blue. And then we did the projections. And then this one was ABUMIP, which is looking at big collapse and big sea level from that. And and you can ask, well, why are you taking so long to kind of do your projection, which is the end of the time? Well, why are we doing so long is because all of the time we are having this dotted line where we're kind of preparing, assessing which CMIP model can you do, like what is a good climate model for projections? How do you transform this climate model forcing into ice-ocean interaction? And so those are all of those dots that are happening in the meantime. And we're also waiting for CMIP to actually do their run. So it's a community that was together for many, many, many years. And it was really cool in the end because we were rewarded by the IGS, the International Glaciological Society, and we received the first Richardson Team Award medal awarded to a group for helping move the community forward. And so, this is recapping some of the things that we had to do. We had to figure a new way to evaluate CMIP models. This is what in red. We had to wait to develop new ice-ocean parameterizations for Greenland and Antarctica. One of the issues, for example, for Antarctica, that's what we have in blue, is that the CMIP models do not go underneath the ice shelf's cavity. And so we have to figure ways to extrapolate. And we are doing all of this work with no money, as Ginny said. So it's all volunteered. And so therefore, the only thing I can do as a leader is basically be the best cheerleader you can ever think of. Then came, we are working so hard, right? Since June 2014. Then came this star. We've moved into my timeline. We're in September 2018. And we're having a workshop that was co-sponsored by NASA and NSF and by some European partners. So during ISMIP, we were trying to raise money for the effort, but we were never having much luck. But sometimes we had luck to raise little money from different groups to actually meet together, and that was really helpful. So this workshop in Sessamheim was one of those where you're in person and you can do so much because you're together, and it's really amazing. And that workshop is, in a way, really, really instrumental to ISMIP 6. Because on the one hand, we've been working for the last 4 years and trying to develop a protocol and for trying to get the community ready to do a coordinated run, have the right files for outputting, like all of those little things that you have to do if you want to do an intercomparison. So, we've kind of run through that and we're ready, but we can't do our projections because we don't have any climate model forcing. The CMIP 6 models are running behind schedule. There is nothing we can do, right? We're totally stuck. On the other hand, the IPCC deadline hasn't changed. It is still, if you do not deliver your paper by December 20, whatever, it is not considered in the IPCC assessment report. So we are totally stuck between those two deadlines, CMIP 6 kind of creeping forward, IPCC not budging. And so we We have to kind of revise what we do. So while the community is kind of revising the protocol and looking at the experiments and blah, 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 my 3 co-chair at the time, Dominique Payne and Eric Laro and I, we go next door and we kind of take this, we write on the table a plan B. Like, what's the plan B? Like, we don't have time. We have to do a run. We don't have the climate models. And so we redid our whole planning like this, and decided that, right, we need to have working backward. This is a deadline. This is how many months we need to do this, 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 and this. Therefore, we can't use CMIP6 models. They're not going to be ready. We have to use CMIP5 models. So if you ever wonder why a lot of ISMIP6 papers use CMIP5, it's because the data was not there, right? In the end, we managed to sneak a few CMIP6 models that were just there because they were just ready, but that was a lot of luck. And the other thing to remember is that ISMIP6, even though there is a 6, it's the first time we're doing this, right? The 6 is linked to the CMIP and not the fact that we're doing it the 6th time. So that was, and then we had to actually tell a community, this is the plan, please don't drop out. And luckily they bought this and they were willing to get along. So then let's think about it. Like, what is behind this amazing group of projections? You have a diversity of ice sheet models that have different types of physics, different types of numerics, different type of doing things, which is really, really important. That is fed by different future possible climate, because we know there is a lot that we don't know in the future climate. And so when we chose climate models, we made sure that they had a good historical run. But then in the future, we kind of sample models that had possible diverse future. And that's what you see for Antarctica, that different climate models can give you very different projected future for the atmosphere, but also locally for the oceans. For example, Pine Island Glacier might look very different from one climate model to the next. And so that's just giving you a flavor about why you need to have an effort in projection that uses multiple climate model at forcing, because you really don't know what the future you're going to have, and why you need to have multiple ice sheet models, because again, if you just only have one, you only sample part of the space. In terms of responses, this is the type of solution that you might get, right? We might get, in terms of projections, you get a diversity of ice sheet models fed by future possible climate. It's going to lead you a wide range in responses and sea level. What we can learn is that in general, in a future warming world, the West Antarctic ice sheet is going to be losing mass. But some climate models say that it would actually gain a bit of mass because there is an increased snowfall and not enough melting from the ocean. East Antarctica is kind of really hard because, again, you're looking at those two big regions where you have a balance between a large potential snowfall and mass loss from the ocean. And then the peninsula is also very different depending on the climate model that you choose. The thing is that it takes a lot of time for ice sheet models to do those runs. And so one of the clever ways that we try to sample different feature is to work with emulators. And so we had Tamsin Edward, who led the emulator part of ISMIP, where she basically trained the emulators on a simulation and was then able to actually project a lot of different scenarios that we couldn't do ourselves because it took too long. And those were the scenarios that would be of interest to the IPCC. So now I look into the IPCC table. So the interesting thing about IPCC is that you can't do any science. You have to assess the current literature. And so so for me, there was an eye-opener to be an IPCC author. I did not want to be one. I was asked to be, I joined halfway through because there was a meltdown in the sea level chapter and they needed to have some help. And that's when I was like, okay, fine. It meant that I had to also stop some of my leadership in ISMIP6 because I can't really lead the ISMIP6 papers and then be the one assessing it. Like, so there is a lot of things with that choice. But what was really interesting is the IPCC chapter is therefore a lot of the sea level numbers is, of course, the emulators of ISMIP6, but also simulation from this other MIP called LARMIP, which is the linear response to ocean, and more. And by more, it will be what is in the literature. If I now look about how the sea level are in relationship to a previous assessment report, what I've highlighted is these models in blue, which is what we call medium confidence models. So basically models that took part in ISMIP, the ice sheets models. It tends to be relatively the same numbers as the previous assessment report. That's what I'm highlighting for both the low emission scenario and the highest emission scenario. In the highest emission scenario, we do have a bit of a higher sea level compared to the previous assessment report, but not that much. And in a way, you can wonder why. Like, why is it the case? Well, if you kind of think that a lot of those findings are driven by CMIP 5 models, then in a way that makes sense, right? You're imposing the same climate forcing, and so it's quite similar. The other thing too is that the difference in projected future climate between CMIP 5 and CMIP 6 is not that different again. So again, you're capturing the fact that the ice sheet response really depends on the climate forcing. Now we got some criticism asking, well, those numbers are too low. There's just no way. Is it because the ice sheet models that you're using, those part of ISMIP, for example, is it because they can't be trusted because they're not dynamic enough, right? It's a fair question. Maybe they can't capture any possible marine ice sheet instability where the ice kind of retreats and collapse. It's a fair question. So for this, we kind of tackle that after IPCC, where we kind of did with ISMIP. This is a run about this ISMIP projections to 2100. Well, what happens if you go beyond 2100? Can you actually capture the fast retreats and potential collapse and this marine ice sheet instability? And the answer is, yeah, you absolutely can, right? So the ice sheet models taking part in ISMIP 6 and taking part in ISMIP 7 are skillful at capturing marine ice sheet instability. So the reason that those numbers are so low is just because we haven't gone far enough into the future, right? Or the climate factors, the climate models have not triggered this potential collapse that you see at 2300. Now, I want to talk about the dotted line, right? This high sea level that we've put. This is now highlighted in red. Those numbers come from, this red line comes from two numbers. One simulation of ice sheet models that has this process called the marine, that can simulate the marine ice cliff instability, and the SCG, which is a structural expert elicitation judgment, where basically you ask a bunch of experts and scientists what they think possible futures are. So there's nothing with this one, there's no modeling, it's just judgments. I took part in that process. It is, I can talk about it, but I won't talk about it right now. But the other reason that these numbers were supported in that dotted line, the other part that kind of went into that dotted line and the thought, we described that in the box 9.4 of this high-end storyline, is the fact, the recognition that maybe there are processes that we can't really capture in ice sheet models. And that could be because either we don't know them or we don't know how to implement them. And in a way, this is reflected by the ABUMIP experiment of ISMIP, which was one of the experiments that we did earlier on to that time scale, which I'm showing here in yellow, in that yellow box, where we kind of saying, okay, we don't know what could cause a lot of collapse in the ice sheets, but we know it's possible. So let's just assume that we remove all of the ice shelves and see what happens. And so you get a very high possible sea level and you do get that collapse. And so that fed into that storyline of this high dotted line that IPCC AR6 has. The fact that you can have higher sea level than projected, this deeply uncertainty that you can have. So then you might tell me, okay, Sophie, this is actually not so cool, right? So we can't have a dotted line that's kind of like maybe questionable. So how do we move forward as a community? Well, I will tell you, I'm sorry, but I model what I know, right? So what are the challenges? How do we make progress for deep uncertainty? in one image, this is Antarctica, the knowledge of Antarctica when my grandmother was born. And in the other image, this is the knowledge of Antarctica when my kids were born, right? So one of the ways that we make progress for the deep uncertainty is more observations of the field. Observations really, really are important, okay? So we need to keep on observing a system because then we know what to put into our model. I also want to kind of make us think about the scale of things. Why is it so hard? What is one of the challenge? Here you see an icebreaker in Antarctica. This is my first time that I went into Antarctica, and I was gobsmacked. You can see around it, basically, you can see sea ice, you can see icebergs, and just try to understand the scale of things. This is a challenge. Like, we're trying to model something like in a few grid box with a few parameterization, all of that beautiful environment that's going, and all of those changes, and the sea ice forming, and the icebergs collapsing, and so there is a lot of this beautiful big scale processes that in nature that's happening that we are all trying to model into our models. And so there's a lot of complexity that we need to understand. And so we need to figure a way to understand what really matters and what doesn't really matter. And that's quite hard. Going into the field really, really helps. Of course, it's fantastic. But the other reason I put that little video is to remind us that going into the field, into the polar region, is challenging, right? You have to go through all of this. It's not just like doing field work in the US, right? It's really, really hard. Now, I really like this figure. Like, what do we know? What are the challenge? The challenge that we have is that we don't know the basal conditions well enough. We don't know the shape of the bedrock, and that is really important for grounding line migrations and our models. We don't really know if the bed is sliding, if they're actually sliding on the bed, or if it's frozen to the bed. And the reason I love this image is also for a lot of different tasks. First of all, it's a credit to your university. And it's really, really nice to be able to kind of show that into your audience. The other thing that I realized today talking to Duncan is that I asked him, do you remember, I use this figure a lot in my talks. I can't remember where it was taken or when it was taken. And so he was able to tell me that it was Totten Glacier from Operation Icebridge. So at that point, I was in the Operation Icebridge team that actually helped design that flight line. So it makes me super happy. And the other reason it makes me even more happy is that it was taken on January 23rd, 2011, which means that that flight line is 10 days younger than my son. So my firstborn was at the same time is as old as this image. So I think it's pretty cool too. Anyway, a rate known unknown that we know as a community, and a known challenge is that we know that the rate at which ice sheet lose mass is controlled by the shape and the condition of the bedrock beneath the ice. And what is super cool is that you have people in your university who work on this. I know that Duncan work on that, and I also know that Benjamin works on trying to understand those conditions. The other unknown is that we know that a lot of the triggers that we are working with, that we're trying to understand, that are going to really, really matter in my projections, is going to be linked to the ocean. And this is really, really hard to be able to represent. All of the fast-flowing ice is usually where the ice meets the ocean. And all of the flight line that you see on the other side is basically where we flew with Operation Icebridge. And so again, what is really cool is that a new university, Ginny and Patrick and Kevin are all trying to understand and better model the exoterminous glaciers, or how you actually improve ice-ocean interaction. This is why I was really bummed about not coming in person, because I was really looking forward to those discussions. But I'm really grateful that I had a lot of fun discussion via Zoom. And I also learned that you have a visitors program, and so I hope I can come and stay a bit longer next time. Now, the one thing is that I always tell my students, what I find fascinating about the field is that observations always drive model development, and vice versa. And many of the discoveries were made by mistake. This is discovery by the Fern Aquifer, also part of Operation Icebridge. At that time, we were making flight line that we were trying to get to the bed, because I was saying, as a modeler, I really need to know what the bed looks like. And then we didn't have any return because actually there was water discovery, impacting the radar lines, and so we couldn't get to the bed, but it was pretty cool. Like, this is a new discovery, and so now the next question is, how do we then put that into a model? And that's a bit more challenging. But this is the thing I love about our field, is that there is still a lot of discoveries to be made. And so despite a lot of progress, known unknown remains. We have issues still with calving, sliding, basal hydrology, rheology, blah, blah, blah. And it's still an area of tons of discoveries. There's a paper this week that just came out that I need to really read a bit more about how you can have tides and glacier earthquakes that really show that maybe there are processes that are still missing that could lead to much more sea level rise. And so basically, it's just a reminder that sometimes we know what we are missing in our models, and sometimes we simply don't know because we haven't seen it yet, or we haven't observed it. But this is why many, many simulations for many, many different ice models are needed. So, okay, how do we reduce uncertainty? How do we go beyond the known unknown? Well, thinking about modeling the past and thinking about using the paleo record and testing our models that way is very important. And this is the work that Ruth and her team is also doing. And so I'm so happy to see that. Now, there is a big question that we are starting to think as a community. Is it the end of model democracy? So up to that stage, up to IPCC AR6, it was always accepted that you should give every participating model the same vote. So one model, one vote. And it was also shown that the ensemble mean was generally fitting better the observations than any single model. So that was the belief in the climate community, and this is what we use as an ice sheet modeling community in our projections. But in IPCC's AR6 and in CMIP6, there was this new generation of models that were too hot, the hot model problem. And basically we questioned that, that maybe you should be able to discount models that you think are not doing the right job, so the fitness for purpose. And so it means that now we can also start looking at this type of question. So what does it mean for ice models, the end of model discrepancy? How would you assign some weights, right? Ice sheet models are much better at capturing the present day. That's what I'm capturing. But there are big questions, like if you're taking present day, like what is present day? What is ice? Like, am I an ice sheet? Am I a glacier? How would you define present day? These are big questions. And so we have a working group in IX trying to look at those kind of questions. You could also say, well, do ice sheet models reproduce the right trends, the recent past? That's another fair question. And so we show with SMIP that actually it's really, really hard. In gray sea observations, those lines are ice sheet models, and half of our ice sheet models don't capture the recent past. But a big question that you have right now is, well, what is the uncertainty in your observations? What observations should you use for how long? Are you supposed to use time series versus spatial patterns? Is it fair, given using the historical record and the last 20 years, given that ice sheet models response time scales is really, really long? And so basically 20 years is just like a blip of a second for an ice sheet. Maybe it really is not fair. And maybe it's not fair because reproducing the historical past is something we should absolutely do, but it also requires knowledge of the historical climate forcing that drove that change. And unfortunately, this is something that we still very much struggle with. So even the input to ice sheet models is something that we struggle. And so until we actually can capture that, even that there's a massive spread. This is that big blue box between the two is the same, right? So basically the uncertainty in our climate forcing is just as big as basically the spread that we are doing into our models. So until, how do we improve, until we improve those historical climate forcing, it's a tough question. We'll be a bit stuck. Now what you can ask is, can calibrating projections allow you to download poorly-performing model simulations? And that's a fair question. And it does work. We can demonstrate that it does work, but then you have the question about which observations do you use. And those are, tons of questions again, as you can see in red. Should we try to, how do you best design multimodal and single model ensembles to capture those observations and these calibrations? Should you try to just emulate everything? How do you start identifying process that we do not know and process that we know? And then again, it was nice to discover from Ruthie that she's starting to think about those questions, and she has a proposal that was awarded for that. And so I'm really much looking forward to what comes out of that space. Just along the same lines, how do you assign your weights? How do you make sure that also maybe you don't bias the ensemble? If we have everybody, if there is a few models that many groups use. For example, ISSM is my favorite model in the world, and it's basically used by many different places. So are we biasing the ensemble by all using the same models? So those are questions that we're asking in my group right now. Is it better to use velocities for assigning weight? Is it better to use ice thickness? Is it better to use both? Can you use model similarity to kind of help give more weight to also models that are dissimilar and making sure that you don't really bias your ensemble? And then looking at grace is another example about, is there an optimal spatial temporal choice for weighting? Are you going to look at the Mascon scale? Are you going to look at the Basin scale? Are you going to and then Basin scale, which Basin scale are you using? Are you going to start doing time series? So lots of questions that are really, really fun. Okay, ISMIP 7, and I'm getting towards the end of my talk. We are a community that's international. The dots represent where we have modeling groups. The red dots, we are always welcoming new members. So if you want to take part, the only thing that you need to do is basically say so and submit some simulations, for example. We have 3 different type of activities. We have Antarctic ice sheet modeling by itself. We have Greenland ice sheet modeling, and we have ice sheet modelings that are coupled to the climate system. We have a scientific steering committee, which is amazing. And we also have focus groups. Those are different ways that you can get involved. We have a focus group that thinks about experimental design, one that thinks about ocean forcing for Antarctica, one that thinks about climate calving as shelf collapse, one that thinks about surface mass balance, observations, sea level and GIA, and ocean forcing for Greenland. This is the figure that we made for this Heising-Simon proposal that we are super grateful for. Incredible, generous effort. I mean, a proposal that allows us to have funding here in the US and also financing our collaborators in the UK and in Norway. And so for the first time, we basically have funds for the core activities. And yeah, that was really incredible. This diagram also reflects our other sponsors, like CLIC, Climate and Cryosphere has always given us money for workshops. So I think we got $2,000 per year, but that's a big deal. It helps us rent a room at AGU as for the meetings. So that's really, really important. And then we have close link with SCAR and of course CMIP, right? We use them as projections. And then this kind of captures who targeted audience is. Key to her work is also making collaborative research. And so right now, GHub is helping us do that because we can distribute our data that way. And we can also show, we share a code trying to help reproducibility. In terms of differences to ISMIP 6, we have a longer time scale. The approach that we are proposing is going to be more come as you are. So coming back to being less constrained in our simulations, because that way we can cover more of the uncertainty. We are also going to make sure that we want, and you can see it this way, right? We're having ensemble support, that's what we mean by that. That we want model simulations to be available earlier to the community so that, for example, the emulation community can start doing some work for IPCC2. So if you are interested in thinking about playing with the model results, this is going to be more open this time around. And then in terms of how much time do we have for everything, Well, time is clicking really, really fast in terms of IPCC R7 and the deadlines. We've been spending the last few years thinking about finding a protocol. That's the dotted line. We are about to start launching a trial protocol run. So we are a bit beyond schedule. Those lines here are when we're capturing, when the CMIP6 data is going to be ready. And so we were hoping that the historical data would be actually already available. And the answer is no, it's been delayed. And the same thing for the fast track. CMIP6 is going to be delayed. So that's why there's a big question mark, and we might have to kind of deliver that. And then we have basically other targets about when we think those timelines are. And so they're still kind of moving. In terms of wrangling, what does that mean? It means that we have to make those kind of crazy spreadsheets to kind of be kind of saying, okay, this is plan A when now we are using CMIP6 data, and this is plan B for when we're having CMIP7 data, and this is when we're using all of the data and blah, blah, blah. And so those you can find timelines and all of those steps in website, which is ismip.org. We do have a fantastic community. It is very open. And so our meetings, the triangles, are always there. And we hope that you can join us either at AGU or AGU. And so in conclusion, rising seas, a known future yet deeply uncertain. I think hopefully I managed to pass that message. I also hopefully managed to kind of change a bit your thought and kind of convince you why now is a perfect time to work on ice sheets and sea level change. It really is, I think, an exciting field in our field right now, in ice sheet science, because on the one hand, there is a questions about how to generate more simulations and more observations and thinking back about model observations intercomparison. On the other hand, there's a question about what can be learned from either the big observational datasets or the big ice sheet model datasets. And so it really is a time for that is full of opportunities and discoveries, full of novel and possible methods. AI can play into that are being developed to make the most of those ice sheet datasets. And by this, I mean both model and observations. It really is a really, really fun time. And of course, you do have a lot of challenges, for example, such as improving polar climate, ice sheet models so that they can reduce the deep uncertainty and ice sheet and sea level projections. But it really, really matters, right? Because in the end, what we're going to deliver as a community is going to then be delivered into tools such as this one from the sea level change team, where we deliver the projections. You can click on any of those dots. You would have sea level rise for different scenarios, and it's being used for stakeholders. I know that I won't be there for drinks tonight, but I do have a challenge for you. I would love for you to kind of talk in the room with you and ask the colleagues, young and old, what they think is exciting, what could be a perfect thing to look at. And so that's my challenge to you. Like, what can you do to reduce its uncertainty in ice sheets and sea level projections? Because some of the methods that you might be using for your research might be applicable for ice sheets and vice versa. So please take that challenge. I can't wait to hear the ideas that come back. And so with this, I will thank you. And I will take some questions, but I guess I should really thank first this amazing community, the ISMIP community. This was the first workshop that I mentioned. That was the launch of ISMIP, and it's a growing number of people, and so yeah, it's really fun. So I hope you can join us too.
Any questions from the audience?
You guys should go for drinks. That's fine.
Thank you, Sophie. A really amazing talk and interesting history of ISMIP. I learned a ton. I'm curious about the detail you mentioned in between the Mickey simulations and this SEJ committee. And I'm curious, like, what is the judgment of those experts?
Yeah. The SEJ is a crazy experience. Basically, I did two of them. You get asked a bunch of calibration questions. And so those are the answer is not really in the detail. So it would be like there is a sea level change in the Galapagos Island. What can it tell you about Greenland? Right. So it was like those kind of like crazy questions. There's somehow a paper linked with it, but there's no answer. There's no direct answer. That's all open-ended questions. And those calibration questions basically help you, are designed to assess what your general knowledge is. So for example, you should know by this example, it would kind of say, well, okay, sea level has a fingerprint. It matters where it came from. Galapagos Island is roughly there. And therefore you can backtrack whether Antarctica or Greenland makes a difference, right? So you can, so it kind of ask you to kind of make this kind of assumptions. And it also asks you to be able to say how certain you are with your questions. So, and your answers. So you need to be really good at statistics, and I'm really bad at statistics. So you need to put the confidence level, like, I think this is this answer plus or minus whatever. So you have those kind of calibration questions. It's very intense because you only have a short time to do those. And then you get the next day or whatever, you get tons of questions, kind of saying, okay, well, what do you think the sea level contribution from Antarctica would be in the year 2050 if you have an increase of CO2 by blah, right? And so, and then divide this by increased runoff and divide that by temperature. Like, so they kind of ask like those really, really random questions. And there's a lot of them. And then you have to kind of say, well, I think therefore sea level will be 5 meters plus or minus 50, right? So you give your thing, your answers. So it's very intensive. And it's very, I struggle with it because I think it also, when you're doing those things and the numbers, in the end, you end up inventing numbers, or you give your best judgment, right? So you're judging what you think is a possible answer. And it's therefore also very much based on what you've read, right? So if you look at the different SCJs, they came after, one of them came after the big new idea about Mickey. And so it therefore influenced people in the room. So the way it influenced me is that I knew then, after the Mickey paper, that maybe it really may help me think about there are many processes that we don't know. And so how do I capture it? Whether or not I thought that Mickey was implemented the right way or whatever, that became irrelevant. But it helped me acknowledge that there are processes that in sheet modeling that maybe we don't know and that could lead to higher sea level. So SAJ, that is kind of weird because it really is a bunch of experts in a room doing kind of like a high school test. It's really intensive on the limited timelines with those crazy questions, but it works well in some disciplines. So it's just, trying to give an answer. Whereas the Mickey that were used in a PCC-AR6, it was a result of only one model simulation, because at that time there was only one model during this type of physics.
Thank you for the insight.
Thank you, Sophie. Really wonderful talk. You mentioned two things that I have like a compound question about. One is the observation that when you did projections to 2100, there was this question of, are you capturing the marine ice sheet instability? And when you look further forward, you indeed say yes. And then you had this question about, well, what observations do we use to try to score which models are doing well? And there have been observations and arguments made that the marine ice sheet instability is already underway in some sectors, in some places. I just wonder, when you see observations like that, how do you think about that in the context of assessing some of these models? And I guess also, how do you identify when you're seeing the signature of marine ice sheet instability in the models? What sort of timestamp gives you that?
Yeah, I love that question. Because I think as a community right now, we don't know. And I can say that, I say that so when I started my PhD, it was it was at the time when we had just started seeing the very much thinning of Pine Island glaciers, the first observations. And then there was a lot of papers saying, oh, Pig is going to collapse, blah, 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 blah. All right. And then as we take longer observations, you move forward in time. Actually, Pig has not collapsed yet, right? And the realization that maybe a satellite observation record, for me, this is what I strongly believe right now, is fantastic, is highlighting the dynamics of ice sheets, but it's actually, I think, too short, right? And that's what I try to kind of say, like, it's really like a blinking timescales compared to the ice sheet timescales of evolution. I think this is something as a community that we need to kind of discuss more, absolutely, about actually the whole value of scoring using observation, and it's very tricky. That maybe we don't have the right time scale yet to do that. And maybe we don't have even the ice sheet model runs long enough. Like maybe we need to have a much longer historical in order to properly assess those kind of things. And as you and I talked about, there is this issue about initialization assuming steady state. Absolutely. That means that we tend to start with an ice sheet model that's really hard to be kicked off and off balance. At the same time, the observations tells us that Greenland was in steady states for many years. For many years, ice sheet models have heard the Greenland ice sheet has been in steady state until 1980, right? So that was fair, as therefore our assumptions to do that was fair. Now that we are learning more, that maybe that steady state actually thing maybe was a bit too strict. Right, this is good to start looking into new development in modeling that allow us to kind of initialize not in steady state, which should be the right thing because ice sheets are never in steady states really with the climate system. So it's therefore, I guess, a bad way to answer to you that those are big questions that we need to talk as a community that we haven't figured out yet. And we all need to become on board with it. So I look forward to more discussions with different people, including you, on that.
Hey, Sophie, this is Duncan. It was a great talk, especially on the infrastructure of science aspects of it. I guess the question is the CMIP models, how do they deal with ice sheets and the potential coupling between the ice sheets back into the global climate?
Yeah, this is cool. So in ISMIP 6, we had proposed coupled experiments because I had talked to climate modeling centers like NCAR and GFDL, and they thought, yeah, we'll be ready, right? We can have Greenland coupled to the atmosphere. We can start doing coupled simulations and we'll be fine. And then in the end, they were not ready. But for ISMIP 7, let me try to see if I can work backward. So we do have this, these guys, right? So right now we have about a dozen climate modeling centers that have been working really hard since CMIP 6 till now to continue their coupling. And so we do believe that there is going to be more simulations of ice sheets coupled within the climate models. And so one of the big stress is the climate modeling community is starting to say, well, coupled ice sheets, like interactive ice sheets are now maybe the norm. And so when we're designing an experiment, should we, instead of having an experiment that says with ice sheet models, maybe we should start saying experiment without ice sheet models, simply because there's becoming more and more ice sheet climate models with dynamic ice sheets models. So yeah, it is happening. Soon you will have more and more climate models running interactively in those big climate models. They still have issues, like it's still really hard, like Antarctica can be still hard. So in terms of like what we call credible projections, we still think that the standalone work is super important, but maybe in a few years' time we'll be out of business because it will all be done within those guys, which will be great too, right?
Sophie, it's Ginny. My question is there any observational gap that you see as being outstanding still in the community?
Yeah, a lot. I would love to be able to time travel backwards. I know it's not possible, but I also understand that there is a lot of photographs that are available. I also really think that the work that you do with understanding better, the outlet glaciers and their relationship with how they move and their environments is super important. And also like not only the actual movement, but also the external forcing. So I think that's a big gap. Always, I will always go back. My first hands down is if we could just nail down the bed, that would be really, really neat. And that's because then it's done, right? It's just, we just need to just go and map it.
Well, you're assuming the bed doesn't change over time. So
Absolutely. And so that's why repeat mapping will be great because it can prove me wrong. Yeah. No. So I really look forward to repeat bed mapping. And the one thing I love learning today about Duncan is the fact that the instruments are the same for a long, long time. So actually doing repeat measurements should actually be quite cool because you haven't changed technology. And so it's not a question about having to kind of
there's a
I hope that
proposal
makes
for you,
sense.
Duncan.
Yeah.
All right. Well, thanks again, Sophie, and we will toast you in our reception.
Yeah, and please tell me the big questions that you came up with.
We will.
Thank you.